This video is on Dalton's law of partial pressures. We'll also be talking about something called a mole fraction. So far, we have discussed things like a container with one gas in it. So how can I word that? So far we have discussed how about properties of a container with a single gas inside. Meaning, we've talked about a container and it's full of helium, for instance. And we may have been discussing the pressure and the temperature and the volume and all of that good stuff. So now, though, the discussion has to get a bit more complicated because we know that there are lots of times when we just don't have one gas in the container. Maybe we have a mixture. And so that now becomes our discussion. How do things change when we have a mixture of gases? So I'll say what changes when we have a mixture of gases instead. So let's say that the container I'm working with now is helium and oxygen and neon, we'll just say. Okay, so it's a mixture of all three. So the big thing that's going to change in this case is the pressure. Okay, so we have to have a discussion about how the pressure is affected because we now have a mixture of gases. Okay, and so now, we're up in this container, the pressure was all caused by the helium. So when we talked about the pressure, and I'm just going to make something up, and we said the pressure was 1.7 atmospheres, let's say. That 1.7 atmospheres was caused by all of the collisions of all of those helium molecules. So now, though, when we talk about the pressure in this container, it's a little bit different because in my mixture container, that pressure that I'm going to discuss would be caused by the collisions of all three of those molecules. So what we start talking about in a container with a mixture is something that we call the total pressure. And it's labeled as P, like sub T for total, okay? So I'll just pick a new number, and let's say the total pressure in this container was like 2.3 atmospheres, okay? Well, that is caused by the helium and the oxygen and the neon, okay? So what we can do is kind of expand our discussion to say the total pressure in that container is a combination of the pressures of all three of those gases, which we now refer to as partial pressures because it's only a partial of the pressure in the container. And the way we write that is like the partial pressure of helium would be denoted like that, okay, because it's the pressure caused only by the helium. So the total pressure in this container is the sum of all three, of all three partial pressures. Okay, so now if I had 5 gases, it would be the sum of all 5 gases, but in this case, I have 3 gases. So this idea is named Dalton's law of partial pressures. Okay, so what Dalton said, let me write this real quick. So Dalton said that the total pressure, I'm just going to abbreviate for P. The total pressure of a mixture of gases is equal to the sum of the partial pressures of the gases in the container. So that is in words what I just showed you kind of mathematically in this equation. Now, if I knew, and let me back up for a second, and notice up here, I'm not really calling it total pressure because I mean, I can, but there's really no reason to refer to it as the total pressure when we know that only the helium is contributing to the pressure. But in this container, it's pretty necessary for me to refer to it as the total pressure because I have 3 different gases. Okay, so now where I might know the total pressure in the container, now again, I just made that up, but so I would know this variable. These 3 pieces are unknown. And so there has to be a way for us to solve for the individual partial pressure of a gas. And it's really pretty easy, and it deals with something that you already know, which is the ideal gas law. So I'm going to, how do I want to say this? I'm going to say that there are 2 ways that we're going to use the ideal gas law when dealing with partial pressure. So remember, the ideal gas law is PV equals nRT. Okay, and so the first one would be to solve for total pressure. Okay, so like up here in my example, if I was looking for the total pressure of this container, okay, how would I do that? Well, I can use the ideal gas law. And if I were to solve this thing for P, of course, I divide both sides by V. So my equation would look like this. P equals nRT over V. Okay. Now, but I'm looking for the total pressure. So if I'm looking for the total pressure in this container, there's another variable in this equation that I have to consider it being the total. And that would be the moles. Okay, because if I'm going to talk about the total pressure in this container, well, then it's all the moles of those gases that are contributing to the total pressure. So I'm going to label N as N sub T now, because if I was going to solve this equation for total pressure, I would have to make sure I knew the total moles that were in that container. Okay, so this is a little bit different. Okay, so that's one way I can do the ideal gas law. The second way is to solve for a partial pressure. So let's say in this container, we were looking for, we didn't care about anything except the partial pressure of, let's say, the helium. And that's what I wanted, okay? I don't want the total pressure. I just want the partial pressure of the helium. What's the contribution of helium's pressure in this container? So I can use the ideal gas law, but this time, if I'm going to look for the partial pressure of the helium and just the helium, then one of my variables, again, is going to be subjected, I guess, to just that individual gas. And that would be the moles of helium. Because, see, if I want the partial pressure of helium, then I don't really care about how many O2 and how many NEs are in there, because it's just the helium contributing to the partial pressure of the helium. So I hope you can see that these 2 formulas, it's the same, variation of the ideal gas law, but we're just taking into account, am I looking for an individual partial pressure and then thus using an individual mole, or am I looking for the total and then have to use the total number of moles in a container? Okay, but again, nothing really new here because this is the ideal gas law. All right, so let's do some practice because I think that is the best way for us to learn this. All right, so here we go. It says a gaseous mixture of 6 grams of O2 and 9 grams of CH4 is placed in a 15-liter vessel at 0 degrees Celsius. I guess that's not a question, huh? That's a typo. There we go. What is the partial pressure of each gas in the vessel, and what's the total pressure? Okay, so let's do some identifying. I mean, we know we have 6 grams of O2, 9 grams of CH4. That's got to be important. I have a 15-liter vessel. That's my volume. 0 Celsius. That's my T. Of course, I'm going to change it to Kelvin. So I'm looking for partial pressure of each gas and total pressure. Whew. So at the end of the day, I want the pressure of O2. I want the pressure of CH4. And I want the total pressure. Okay, so if I'm looking for each individual pressure, then I'm going to have to focus solely on the O2 and solely on the CH4. So if I'm going to do the pressure of O2, Okay, just like up here. I'm going to solve my equation. It's going to look like moles of O2 times R times T divided by V. And basically, I'm just going to plug everything in and be done. Okay, and same thing with the CH4. But this time it would be the moles of CH4 times R times T divided by V. Okay. Now, I don't have moles, but I do have grams. So this is a quick, just conversion. So if I take my 6 grams of O2, O2's got a molar mass of 32. I didn't leave myself a whole lot of room here. Let's see. Let me crunch that out. So 6 divided by 32, 0.1875 moles of O2, and then I'm going to need to do the same thing for the CH4. So let's see. 16.042 divided by. All right, and we get 0.56. We'll say 10. And so from here, I just plug everything in. Okay, so I have moles. Now let's have a discussion about R, okay, because this problem did not specify a unit, and it doesn't matter in this case what value of R I use, because whatever value of R I use, I'm going to get that pressure unit out of it. So it doesn't matter. This is a case where because it didn't specify, you can pick, and you're either going to get an answer in ATM or you're going to get an answer in KPA, and that's fine. So up to you. I'll use the 8.31 because students seem to like that number. I don't know why, because it's not a decimal. I'm not sure. Okay, and then my temperature, of course, 0, so 273 Kelvin. And then my volume was 15 liters. Look at my units. Liters cancel. Moles cancel. Kelvins cancel. I'm left with KPA. I'm going to do the same thing for my bottom problem. Notice the only thing that's different is the number of moles. So this is really just a lot of number crunching. Forgot my unit. Okay. And I'm going to have to punch this because I did not do it. And for the first one, I get something like, now sig figs here would be important, should be 3, so 28.4 kPa was the partial pressure contribution from the O2. And then the combination from CH4 is 84.8 kPa. And then for P total, now there's 2 ways you can find P total. So think about this for a minute. I could do this, where I'd have to add my moles together and crunch all that in there. However, if we go back to this conceptual idea that the total pressure is the combination of all the partials, then all you have to do is add these 2 together. And maybe you were in ATM, and that's okay as long as you're in the same unit. And so the total pressure in this container would be 113.2 kPa. Okay, so that's how you can do a problem with partial pressures. And let's do one more. What's the total pressure exerted by a mixture of 2 grams of H2 and 8 grams of N2 at 273 Kelvin in a 10-liter vessel? Okay, so this one's just asking me for total pressure. So PT is NT times R times T over V, and we see quickly that I just need to solve for moles, plug everything in, and I'll be done. So 2 grams of H2. Well, that's almost 1 mole, right? oops, and then 8 grams of N2, 28.02. Okay, so if we crunch this, oh, and then that's an 8. And so then I'm looking for in total, right? So I just have to add those two together, 0.9921 plus 0.2855. So this question did not ask me for the individual partial pressures. It only asked for the total. So because it only asked for the total, I just added everything together. What was my volume? 10 liters. Again, up to you what unit you want to use, because it doesn't specify. So you can pick. And here's where I'll round finally to my, let's see, I should have three, hold on. Oh, sorry, I thought I made a mistake. Okay, so when I add that, or when I crunch that number to 3 sig figs, I get, 290. That's only 2 sig figs, but we'll leave it. Or 2.90. There you go. times 10 in a second. Is the total pressure in that container. And again, that question was a little bit different because it didn't ask me to find the individual pressures, just the total pressure. So that is how we do partial pressures. And again, it's pretty much just a deviation of the ideal gas law. Okay, so one more thing, and that is something called mole fractions. So this is a little bit interesting. I'll show you a derivation real fast, but it's basically just another formula. So in a container, if we have a mixture of gases in the same container, okay, the volume and temperature remain constant in that container. So if I were to do a ratio, so like let's say I'm just going to call it gas 1. So if I had the pressure of gas 1, which could be found by taking the moles of gas 1 times R times T divided by V. Okay, if I wanted to do a ratio of that to the total, oops, that was too high of a line here. If I wanted to ratio this to the total pressure, which can be found by taking the total moles times R times T divided by V. What we quickly see is that we're going to have, because R, T, and V are constants, they drop out of this equation. And so this is basically, like I said, a derivation. It's me showing you how we end up with this formula. But there's a second formula that says this: the partial pressure of one gas in the container divided by the total pressure is equal to the moles of that gas in the container divided by the total moles. And this is what we refer to as a mole fraction, okay? And it's a mole fraction, of course, because it's the moles of one of the gases divided by the total. And that's the way you get a fraction for anything, right? If we wanted to know the fraction of students in our class who have blonde hair, well, it would be blonde-haired people over the total people in our class. So this is called a mole fraction. It's not confusing. It's just the moles of one gas over the total. Now, how could we use this? So one more practice problem. It says a 4-liter vessel containing N2 at STP and a 2-liter vessel containing HE at STP are connected by a valve. If the valve is opened, allowing the two gases to mix, what's the mole fraction of the helium in the mixture? Okay, so before, I'm a big believer in drawing a picture, but before we even do that, it's asking me for the mole fraction of HE. So what's it want? Well, it wants the moles of HE over the total moles. That's all. Okay, that's all this problem wants. So now let's draw a picture. So I have a 4-liter, I'm just gonna draw a circle, a 4-liter container. It contains N2. It's at STP. Remember that's important. That tells me the pressure is 1 atm and the temperature is 273. And it's connected by some kind of valve to a 2-liter container that contains helium. That's also at STP, right? Yep. So pressure is 1 atm. Temperature is 273, and I just thought of a shortcut, and this is pretty cool. I just thought of the fact that because this problem occurs at STP, we know that we can use molar volume in this case. And so this is one way to solve this that's going to be way easier for us. So because STP occurs, remember that at STP, 1 mole is equal to 22.4 liters. Only at STP, but that's okay because this problem is at STP. So I can solve this by saying, okay, so again, I want the mole fraction of helium, so I need the moles of helium. Well, if I know that I have 2 liters of helium, and I know that 22.4 liters is equal to a mole, that gives me this number. Okay, so that's the top of this fraction. And this is actually a loaded question. I would love to really go in depth with this, and I can in a minute. And then I need to know the total moles, which means I need to know the moles of nitrogen. So I can do the same thing. Should be double that amount, right? So here's are the moles of nitrogen. So then what I really want is total moles. So I add those two together. And it gives me 0.2679 moles total. So this is my mole fraction. I mean, but they probably want me to simplify it. So it gives me 0.333. So what's that? What that truly means is that a third, right? That's a third of this mixture is helium by moles. So there you go. That's how you could solve for a mole fraction. Now this problem is so interesting because if you didn't use this, you can still solve it, but think about it. If you didn't use molar volume, the other way to solve this problem would have been using the ideal gas law to solve for moles, and it just would have been more work. You would have had to solve PV nRT for this container, PV nRT for this container, and then filled in my numbers here. But you would have arrived at the same answer, which is pretty cool to think about. The third piece of information in this problem is so crazy because once you open this valve, right, a lot of things are going to change. The temperature might change, the pressure might change. Okay, the volume, of course, changes because now the gases are occupying the whole amount. However, something that does not change at all is the moles, right? Once the moles are in that container, the moles are there. And so because I could solve for moles beforehand, and then I open that valve, the moles stay constant. So what a loaded question, what a loaded discussion there. But that's how you could solve for a mole fraction.